So TFHE, okay, it's not that easy to have a crash course on it. So it's quite complicated, but I'll try my best. So first, this is the content that I'll be following throughout the presentation and the talk. Yeah, I'll start, of course, with what FHE is, and then we will see how an FHE scheme look like, and then we will see a couple of types of ciphertexts that we will be dealing with, and of course the noise growth problem, the problem where everything begins, and a proposed solution from Gentry. Then we will introduce some useful tools to construct our TFHE scheme, and then I will conclude my talk. So first, what is FHE? I mean, I'm sure you saw this like every day in all FHE events. FHE is an abbreviation for fully homomorphic encryption, and it's a type of encryption scheme that enabling us to perform computations on encrypted data. Because normally, all the computation we are dealing with are on plain text data, like on Web 2, even in Web 3. But thanks to FHE, we are able to perform computations on encrypted data as well. So how does an FHE scheme look like? So this is a public key setup, but of course, you can construct a private key setup as well, which we will do at in the upcoming slides. So we have a encryption algorithm E. We have a key generation algorithm based on this encryption scheme. Of course, encrypting and decrypting functions. And additionally, we have an algorithm called evaluate. And this evaluate algorithm will make us perform our computation on encrypted data. And it takes a public key, a circuit which we want to apply to encrypted data, and some permitted set C sub E of circuits that we are allowed to perform our functions. And of course, we are given some ciphertext, Psi1 to Psi-n, and we will combine these ciphertexts to output another ciphertext according to the circuit that we are dealing with. So of course, the computational complexity must be in polynomial time, and if this encryption scheme E is correct for all circuits in C sub E, for any key pair, of course, we are totally allowed to perform our functions on encrypted data. So it starts with a number of ciphertexts, like Psi1 to Psi-n, and when we apply our evaluate function, which takes a public key, the circuit that we want to apply, and the set of ciphertexts, the capital Psi, and it outputs another ciphertext, which is totally equal to decryption of it outputs a ciphertext, and when you decrypt that ciphertext, you obtain the output of the circuit applied to plain text version of ciphertext. So okay, so let's have some ciphertext, and let's consider addition. And we have two ciphertexts, A and B, and let's assume these A and B encrypts 3 and 5. Normally, we add 3 and 5 up, and we have 8 in the plain text computation, but FHE allows us to go for it in encrypted versions as well. Like, we can add A and B up, and we have the encryption of 5. So this is basically the mathematical formalism of what I've tried to explain, and we will see the more details in the upcoming slides. So first things first, we start with LWE. LWE stands for learning with errors, and it's a mathematical problem based on the idea of representing an information, a secret information, as a set of vector equations, and to that equation we add some small element which we call it noise, and that noise makes our vectors not easy to decrypt without having the secret key. So this is the basic equation. A is a mask vector which chosen randomly, and S is a secret key, E is the noise, M is the message, and delta is the scaling factor, and that scaling factor stands for Q over P, and this Q is the modulus of ciphertext space, P is the modulus of plaintext space. These moduli are different because usually ciphertext space are much bigger, just to allow noise to contain and not to disrupt the message. And we're taking the inner product of the vector A and the vector S, which is secret key, adding the noise, adding the message, and then we have the B. So, and at the end of the day, the pair A and B is our ciphertext. So this is regular learning with errors, but we have a different version of it, RLW, which is called ring LWE, or ring learning with errors. In normal LWE, we have vectors, but normal FHE scheme has to allow multiplication, right? But when you multiply two ciphertexts, you multiply two vectors, but multiplication on vector space are not defined. So we need something else. And we have RLW. And here, B, A, S, E, and M, everything is polynomials from a polynomial ring. And these polynomial rings are modulo some ideal, like x to the n plus 1. I don't know if you're familiar with ring algebra, but so basically we're taking polynomials and taking modulus of those polynomials with respect to x to the n plus 1. So for instance, if n is 2, then the modulus is x squared plus 1. Then in this set of polynomials, x to the 3 plus 1 is the same thing as x, because we're dividing it by x squared plus 1 and getting the remainder. And we have one more thing in terms of ciphertext types. This is our GSW, ring at GSW. And this image is taken from Ilario Lodi's presentation. And Ilario Lodi is also one of the co-authors of the FHE paper. This is, of course, a bit complicated compared to others. We have a three-dimensional matrix, and I don't know why we cannot see the bottom, but that's okay. So these A, B's are the same polynomials, like same kind of polynomials, let's say, and they represent the ciphertext. But this is useful for us because of the reason that we will see in a couple of slides. But it's good to know the ciphertext types because these three ciphertext types are the main ingredients in TFHE encryption and decryption. Okay, this is where everything started, the noise growth problem. LWE is based on adding noise while encrypting. Okay, this is good, but a fully homomorphic encryption scheme must allow infinitely many of computation. But when you perform a computation on a noisy ciphertext, you add more noise. So when you perform computations over and over again, and at some threshold point, the amount of noise exceeds the threshold, and then the ciphertext becomes indecryptable. So okay, we needed to find a way to get rid of this problem and to control the noise growth. So silly idea would be to decrypt the ciphertext and encrypt encrypt with another secret key and have fresh encryption. This is silly because we don't want to decrypt. We want to do everything without decrypting. Better idea to encrypt the secret key and use that encrypted secret key to evaluate the decryption circuit of the encryption scheme into the ciphertext. So let's see how it does work. Okay, this idea is proposed by Gentry in 2009, Craig Gentry. So let's suppose we have an encryption scheme E, and our plaintext space 0 and 1. So we're working with bits, basically. And we have a ciphertext, psi1, and that encrypts pi under pk1. And we want to refresh it. Let's assume like we did several computations, and the noise is a bit in the dangerous level, and we don't want to lose our ciphertext. We want to refresh it. So to decrypt it homomorphically, let's suppose we have another public key 2, corresponding to another secret key, and we're encrypting our ciphertext with using our new public key PK2, and we also encrypt our first secret key by using the same public key and take the bits of encrypted secret key. And now, using the homomorphic property of our encryption scheme, we can decrypt a new ciphertext using the bits of encrypted secret key. So what we are doing essentially here is, okay, we had the plain text, we encrypted it, we have a ciphertext, we did several computations with it, and the noise is about to exceed the threshold level, and now we're adding one more encryption layer to it, and we're decrypting the new ciphertext using the bits of encrypted secret key, like the first secret key. So, and this allows us to have a new ciphertext with only the second encryption layer. So we're just taking out the first layer. And of course, all the noise came with it. And this is helpful if the decryption circuit is less noisy than the other noisy operations. So this was the main idea Gentry proposed, and it was genius, but it was not quite applicable in that time. But throughout the last 15 years, things have changed really, really well, and now we have several implementations. So okay, before moving forward, here is the part where I want to introduce some tools that we use to construct TFHE. First is CMUX. It stands for Ciphertext Multiplexer, I think, yeah. And it's basically used to conditionally select between two encrypted values. Okay, assume we have two encrypted values, like D0 and D1. And we have a control bit, B. It's either 0 or 1. And we want to choose one of them. But and we can do it by using, I don't know what. We need to see. Okay, maybe yeah. Maybe I can do it like this. Okay, so something like this, like in normal arithmetic, would solve the problem, right? If B is 0, then we have D0. If B is 1, then we obtain D1 from this equation. So this is the where intuition might come up. Yeah. Okay. Awesome. And this is the essential tool that we will use. So, and one more thing, we want to rotate some polynomials because we were working with polynomials, right? We're working with RLW ciphertext and also RGSW ciphertext. And suppose we have a polynomial m of x, and it could be the message itself. And if you want to rotate this polynomial by, let's say, p positions, we basically multiply it by x to the minus p, right? Because these are modulo x to the n plus 1. When you multiply it x to the minus p, we will have m0 times x to the minus p, m1 times x to the 1 minus p. And when you arrive the pth position, you will have x to the p minus p and x to the 0, which will be 1, and the coefficient will get on the top. So why are we doing this? Basically, the idea is, in TFHE, we want the message to be in the most significant bits. So the most significant bits on the left-hand side, and we want the noise be contained on the right-hand side. So, or least significant bits. So to get the message to the left, to the most significant bits, we want to rotate our polynomial. This is why we want to rotate polynomials. Okay, this is good, this is effective, this is useful, but the problem is P is public here, and we don't want to reveal anything. And that's why we use something we call blind rotation. And blind rotation is actually the same thing, but using CMUX to have it privately. Again, we have a message polynomial m of x, and you want to rotate it of p encrypted positions. Okay, so basically we will multiply it by x to the minus p, but we don't know p. So we represent p in the binary form. So all p0s to pk's are either zeros or ones, and the others are, it's just sort of a linear combination of binary. And our Cmax, if pj, any pj in index here is 0, then it will output m. If it's 1, it outputs x to the minus 2 to the j. So at the end of the day, when we multiply the message by x to the minus p, we get exactly the pth positions coefficient at the left, at the most significant bits. This is the idea, but this is not a one-time process. It needs an iteration, which we will see. And now, using these useful tools, we will construct bootstrapping on top of TFHE. So we saw that what Gentry's idea was, like to decrypting, like applying decryption circuit homomorphically, right? So our inputs here will be a LW ciphertext, C, and indices are A and B. A is a vector, B is a scalar, and it encrypts a message M, let's say. And we need something we call a bootstrapping key, and it's essentially the encrypted secret key bits, which we also mentioned. And the important thing is it will be in the form of RGSW ciphertext, because it's more useful and it's actually the most efficient way. And the other thing, of course, the layer 2, not blockchain layer 2, but the second layer encryption. We RGSW encrypt the LW secret key S, as I said, and under new ciphertext S prime. And using all these, we compute what we call phase, and it's actually B minus A dot S. And if you recall the encryption equation, it was B is equal to A dot S plus epsilon or noise or E plus message, right? So if we can calculate B minus A dot S, it's actually message plus noise, right? So, or noisy message. So now, after having this phase, like B minus A dot S, we want to blind rotate this polynomial and to have the noisy message. To do so, we first start with x to the minus b. Why? Because we have b minus. Sorry, we want to delete the effect of encryption, and that's why we have minus b plus a dot s. A dot s is a0 times s0 plus a1 times s0 plus a2 times s2, and goes like that till an times sn, right? So we start with minus b, and then x0, a0, s0, and then we'll move like that. So we start with multiplying our message, or sorry, not message, the ciphertext by x to the minus b. V here is RGSW encryption of our ciphertext, so the second layer encryption, and we assign this multiplication as v0. Why not? And this is the first input to Cmax, the ciphertext multiplexer, and this Cmax takes the encryption of the bit S0 of the first secret key and takes V0 and V0 times x to the A0, and it outputs the RLW encryption of V1. And this is V0 times x to the A0 S0. So we keep moving, we keep doing this until the final element and until we have n Cmaxes. And at the end of the day, we have something like this. So we start by x to the minus b, and then multiply by x to the a0 s0 till a to the x to the a n minus 1 s n minus 1. And when you multiply all these, as b minus a times s is equal to the noisy message, we have the noisy message with minus sign, right? And this is a good illustration to explain this concept. So at the end of the day, we have a noisy ciphertext, and we encrypted it with using the new secret key as prime. And then we decrypt it homomorphically using the encrypted bits of the first secret key, the same idea as Gentry proposed, and that allows us to come up with a new ciphertext, but the message is in the most significant bits, which means less noise. So this is the basic idea behind TFHE bootstrapping, because having the message in the most significant bits means that we have much more space to noise to accumulate. So this is basically the idea behind it. And I think I have 5 minutes. So that's why we're doing this. And this is okay. I think maybe you realize that I haven't touched where we handle this delta m plus e step, because I knew that I wasn't gonna have enough time to do it. But you can check check notions called sample extraction, key switching, and modulo switching. And I think after all, having these notions as well, it will be a complete guide for TFHE. I just wanted to give the intuition behind bootstrapping and the TFHE bootstrapping in this talk. So it's basically it. And if you have any questions, I would be glad to answer.